Hi, you are welcome back to the Twitter 10 channel. In today's lesson, I'm going to help you to understand the basic concept of the conditional probability, and after which we are going to do a lot of exercises, and I'll drop these exercises in the same playlist for you to get the concept very well. Now, when we say conditional probability, what are we talking about? So we are saying that when we have two events such as A and B having a sample space S with the probability of B being greater than 0, know that A is an event, B is also an event, but this time we already have the probability of B. That means B has already occurred. Then we are saying that the probability that event A will occur given that event B has already occurred is the conditional probability of A given B. And this is denoted by the probability of A given what? B. Mathematically, we will say that this is equal to P of A intersection B out of probability of B, where the probability of B must be greater than 0. Because if this is 0, the equation becomes undefined. So from here, let us break the formula down for you to understand. Now we have P of A and B is the conditional probability of A given B. Then we have P of A intersection B is giving us the probability of A and B occurring together. Then finally, P of B is equal to the probability of B that has already occurred. In the same way, we can change the variables, and when I do that, then I'll get the conditional probability of B given A is giving me P of B intersection A, all dividing the probability of the event A, given that the event A must be greater than 0. Note that the probability of A intersection B is the same as the probability of B intersection what? A. These two events, they are the same. So in our first theorem, let's talk about mutually exclusive events. So I wrote when event A and B are mutually exclusive. Okay, what is the meaning of this? When two events are mutually exclusive, it simply means that these two events cannot occur together. Put that in your mind. The two events cannot occur at the same time. What this means is if event A occurs, then event B cannot occur. In the same way, when event B occurs, then event A cannot what? Occur. So in other words, we would say that the occurrence of one event excludes the occurrence of the other event, and vice versa. Do you get it now? So let us see an example. For example, I have a coin, okay, with a head. So let's use tossing a single coin. Can be an example of what? Mutually exclusive event. We know that we have the head and we have the tail. Now when I toss the coin, the event head and the event tail cannot occur together. It's either you are getting a head or you are getting a tail. If you get a tail, there's no way you can get a head. Okay, do you understand? And if you get a head, there's no way you can get a tail happening together. Do you understand now? So that is an example of a mutually exclusive. So let's dive into that. Now, because the two events cannot happen together, their intersection is always equal to an empty set. So we can say that A intersection B is equal to what? An empty set, or is equal to what? A null set. Why? Because an intersection of two events means that they have members that are common. Event A has a member, event B has a member, and they are common. And because these two events cannot happen together, they do not have any members in common. So their intersection is always equal to what? A null set. Look at this example. Assuming I have the set S, giving me the members 1, 2, 3, 4, 5, 6. Okay, and I have the members A giving me what? 1, 2, and 3. And I have B giving me, let's say, 4, 5, and 6. These two events, though they are all in the same sample space, they do not occur together. So we can say that A intersection B is a null set because there is no members here that are common. Do you understand now? Now, what will happen if we take the probability of A intersection B? Now, from the first explanation, we learned that A intersection B will give us a null set. What will happen if I take their probability? So watch, the probability of A intersection B is equal to 0. This means that the probability of both events happening together is 0 because they don't have any members in common. Now, when we switch to conditional probability, then we say that the probability of the event A as B has occurred, remember that I'm dealing with two events A and B, is going to give us the probability of A and B occurring divided by the probability of B. Know that I am conditioning on what? B. That's why I divided. If I interchange the variables, I'll condition on A. Okay. Now, you could see that because the intersection is 0, the probability of everything here is equal to what? 0. And why am I saying this? Know that the definition of probability says that it is equal to the number of favorable outcomes divided by the total number of what? Outcomes. And since we don't have any favorable outcomes, A intersection B, we don't have any favorable outcome, the probability of this entire thing will give us what? 0. Therefore, we can finally conclude that in mutually exclusive events, when the event A and B occur together, they will give us what? A null set. When we take the probability of the event occurring together, okay, we are going to get the probability of what? The null set. Do you understand now? Which is going to give us what? 0. So this is mutually exclusive event for conditional probability. Okay, now look at theorem 2. I wrote that when any of the events is contained in the other. Now, if B is contained in A, then we are saying that A intersection B is equal to what? B. This means that if B has members that is found in A, then when A and B occur together, the result should give us what? B. Now, look at this scenario. Let me use it to explain. What if I have the event A like this with its members, and let's say we have event B here with its members found in event what? A. Let's assume that we have 1 here, we have 2 here, we have 3 here, we have 4 here, we have 5 here, we have 6 here, and we have 7 here. We could see that the members of B are 5, 6, and 7. Now, what are the members of A? We have 1, 2, 3, 4, 5, 6, and 7. Now watch. A intersection B is giving us the members that are here and at the same time what? Here. So we have 5, 5, which is here. We have 6, 6, and we have 7, 7. So we could see that the result that we have is the same as the members in event what? B, which explains this reason. So if B is contained in A, then A intersection B should give us what? B. When you interchange the variables and put A here, you have the same what? Result. So A intersection B should give us what? A. Do you understand? Now let's take the probability. Now when we take the probability of this result, then we have the probability of A intersection B is giving us the probability of what? B. Now when we take the conditional probability, what will happen? So P of A as the event B has occurred will give us the probability of A intersection B dividing the probability of what? B. So from here, P A intersection B is the same as the probability of what? B. So we have P of B should give us what? The same P of what? B. When we divide this, the result is 1. So this theorem says that when event B is contained in A, then whenever event B must occur, A must certainly what? Occur. So let me put that on the board. So there you have it. Let's move on to the next theorem. Now, in our theorem 3, we will talk about independent event. When A and B are independent, what does it mean? We are saying that when the two events are independent, it simply means that the occurrence of the first event has no influence on the occurrence or the non-occurrence of the second event. This means if event A occurs, it doesn't have any effect on the occurrence of event B or non-occurrence of event B. Whether event B occurs or not, this one has no influence or effect on this. In the same way, the occurrence of event B will have no effect on the occurrence and non-occurrence of event what? A. So in a nutshell, we are saying that the event A and B do not influence each other. So now we can say that the probability of event B as A has occurred will always give us the probability of the event B itself, because the A will have no effect on what? B. In the same way, the probability of A as B has occurred should give us the probability of what? A itself. Do you understand it now? So this is what we call independent event. Now let me give you an example. If we are tossing two coins at the same time, if I toss the first coin and I get a head, and I toss the second coin and I get a tail, or if I toss both coins together and I get a head here and a tail here, the occurrence of event, the second event that gave me tail, will have no influence on the occurrence of the first event. Okay, so what this means is that whatever happened in the first event is not going to influence the second toss or the second event. If I got a head when I tossed the first coin, it doesn't mean that head was the one that influenced the second event for us to get a tail. Do you understand now? Or imagine you are playing a Ludo and you have two Ludo die. Once you roll the first die and you get a 5, and you roll the second die and you get a 2, the events are independent on each other. The first 5 did not influence you getting the 2. Do you understand the concept now? So that is all about independent events. Now, when A and B are dependent events, then it's very simple. That was what we spoke about from the very beginning. It means that the probability of event A will surely have an effect on the probability of what? Event B. This means that anytime any of the event occurs, it will affect the other event we are looking for. So this is just the first point that we spoke about, that the conditional probability of A given B is always equal to the probability of what? A intersection B, all out of the probability of what? B, where the probability of B should always be greater than what? 0. So this is a dependent what? Event, because one will surely depend on the other for it to occur. So that will be all for theorem 4. So let's move on to theorem 5. In theorem 5, I will talk about the multiplication rule. From the conditional probability of our first rule, we learned that the probability of event A as event B has already occurred gave us the probability of A intersection B dividing the probability of what? B. Remember that the probability of the event B here should be greater than 0. Now, if I divide this by 1, I can cross multiply here. Don't show this. So this will multiply this, giving us the probability of A intersection B is giving us what? Probability of B times the conditional probability A as B has occurred or given B. And this is what we call the what? Multiplication rule. So if I want to find the other one, then I can just interchange the variables, because the probability of A intersection B can also give us the probability of event A times its what? Conditional probability. Do you understand? The reason is that this and this are the same. Even if I put B here and I put A here, the results are the same. So I don't need to write it this way. So this is what we call the multiplication rule of the second event. That will be all for this one. So let's talk about what if we have multiple events, like 3 events occurring at the same time. Now, what if we have 3 events? Event A, event B, and event C. From this, we can apply the same multiplication rule. From the multiplication rule, we learn that if the events are 2, we have this that we have here. Now look at this. For 2 events, we take the event of A and B occurring at the same time times the probability of B times its conditional probability. But if the events are 3, what are we supposed to do? Then we have the probability of event A intersection event B intersection event C, and this is going to give us the probability of event B. I'm using the same formula to deduce this. So the probability of event B times its conditional probability A as B has already occurred times the conditional probability of event C as A intersection B has already occurred. So let me put this in a square bracket. Now, this should not confuse you, because this we have here is an associative law, which says that when I have A intersection B intersection C, then the result will be equal to A intersection B intersection C. So that even if I interchange them, I should get the same result. So when I take A intersection, the intersection of B and C occurring at the same time or occurring together, it should give me the same result as when I take the intersection of A and B, their intersection with C should give me the same result. Do you understand? So therefore, the probability of A intersection B intersection C should be equal to probability of A intersection B intersection C. Do you understand? So when I take the probability of this, it should give me this result. So from this explanation, what we are saying is that the probability of the event B should not be equal to what? 0. And the probability of what? A intersection B should not be equal to what? 0. If not, the event will not occur. So I think that will be all for this one. There are some other theorems that I didn't talk about. So that will be all for now. There are some other theorems that I didn't talk about. I don't think we'll be meeting questions under these ones, but for now, this is all we have. And in our next videos, we'll be taking exercises under these same theorems to get the basic concept very well. And so that will be all for now, and I will see you in the next one.